Welcome. This video is going to continue looking at solutions to the Section 1 problems of Chapter 1, starting with question 5. In question 5, you've been asked to balance some more equations, and you've also been asked to include state symbols. And this early, the state symbols are a little bit tricky. So let's start with the balancing. KNO3 to KNO2 plus O2. So the only thing I want to balance is the oxygen, and the smallest number I can use here to balance it is a 2, which means I'm going to need a 2 here to balance the K and the N. And at that point, I have 2, 4, 6 oxygen on each side. I've got 2 potassium and 2 nitrogen, so I'm all balanced up. The second one, I've got calcium carbonate with sulfuric acid. Oh, I should go back to A. So how would I know that these two are both solids? Well, because they're ionic compounds, if it's not mentioned they're in solution, or if water's not part of the equation, then they're likely going to be in their solid state. And oxygen, of course, at room temperature should be a gas. So then CaCO3, calcium carbonate with H2SO4. Since they don't tell us that it's an aqueous solution, I'm going to assume the calcium carbonate is in its solid form. H2SO4, the H is my tip-off that this is an acid, so it's going to be aqueous. And then CaSO4, CO2, and H2O. The CO2 I know is a gas. The water is likely going to be a liquid unless there's a lot of heat going on with this reaction to cause it to be a vapor. And then the CaSO4, it's an ionic compound, so it's either going to dissolve in water or not dissolve in water. And so this is what they're referring to when they said you may have to look up their solubility on a chart. So you're not expected to memorize this. And if you look it up, you find out that calcium sulfate is insoluble in water, so it would be a solid or a precipitate in there. So as far as balancing it, I've got 1 calcium on each side. I've got 1 sulfate on each side. And I've got what I've got is a double replacement reaction. So the H2CO3 has decomposed into H2O and CO2. So if I take a close look at this, I see it's actually balanced already. On letter C, I have Li plus H2O gives me LiOH plus H2. And again, if you think of H2O as really being HOH, you can see that 2 hydrogens have broken off, but only 1 OH group. So I'm going to need a 2 here to balance it, and a 2 here. And so then when I take a look at that, I've got 2 lithium, and now I've got 2 water molecules on the right side, so I also need a 2 on the reactant side. Lithium metal is going to be a solid, whereas water is going to be a liquid at room temperature. And then H2 is going to be a gas, and the LiOH in this case will remain aqueous. And again, not something you're expected to know right now. On D, they tell you that both reactants are aqueous. It's a double replacement reaction. So that means one of the products is going to be soluble or aqueous, and the other one's going to be insoluble. So you could look this up, and if you look it up, you'll find that the sodium nitrate is aqueous, whereas the PbCl2 and lead and chlorine both often form insoluble compounds, or the precipitate, and they do in this case. So then balancing it, it's the NO3 and the Cl that are out of balance, and so putting a 2 in front of each of those balances it up. The combustion reaction, C3H6, you need to know a little more about alkanes to realize that that's propane, so it's going to be a gas. O2 will be a gas, CO2 will be a gas, and in combustion reactions, again, it depends on the heat. H2O could be a liquid or a gas. In this case, it'll be a liquid. Often when you start with a alkane that's in the gas form, then H2O will be a liquid. If it's something like octane, where it starts as a liquid, oftentimes that creates enough energy, those bigger alkanes create enough energy that the H2O becomes a gas. So balancing with my usual method, I'm going to balance the carbon, so put a 3 there. I'm going to balance the hydrogen and put a 3 there. And so when I look at my oxygen, I've got 6 plus 3 is 9, so I need a 4.5 here. So once again, I'm going to double this to 2, 9, 6, and 6. So So then moving on to some of the later questions in this section. Question asks about, says, a mixture of two gases, X and Y, which both have strong but distinct smells, is released from across the room. The smell of X is detected more quickly than the smell of Y. So if I draw a little sketch here, what I have is X and Y being released, and Y, I believe it was, no, X is detected more quickly than Y is. So this one is more quickly, this one's slower to get across the room. So what you should remember is that temperature is really an indication of kinetic energy. So since they're both in the same room, the kinetic energy is the same for both of these gases. What's different then is that kinetic energy is found by m1/2 mv squared. So I know that X moves quicker. So if X moves quicker than Y and kinetic energy has to be the same, the only way it can be quicker is to be lighter, which means Y is heavier and slower. Number 7 asks, it says, ice floats on water. Comment on why this is not what you would expect from the kinetic theory of matter. Well, the kinetic theory of matter says that as substances move from the gas state to the liquid state to the solid state, the particles get pulled closer and closer together. And the only way ice can be less dense is if those particles move further apart as they go from the liquid to the solid state, which in fact they do, and it makes it a highly unusual substance in that respect. Question number 8 asks about phase change. It says a closed flask contains a pure substance, a brown liquid that's at its boiling point. Explain what you are likely to observe in the flask and distinguish between the interparticle distances and the average speeds of the particles in the two states present. So you have a brown liquid. This is number 8. Brown liquid at its boiling point. And so if you think about a time temperature graph for something going from its liquid state to its gaseous state, this is the boiling point right here. And this plateau, and this is true for any phase change, this plateau means that the kinetic energy remains the same. Doesn't mean energy is not going in, because time's continuing and absolutely energy is going in, but kinetic energy is not increasing. On the other hand, in order to move from being in a liquid state to a gaseous state, the interparticle distance absolutely has to increase. So I'm going to answer the second part of this question first. The interparticle distances will increase, but the average speeds of the particles will not increase until it reaches this point right here, and now both the interparticle distance and the speed can increase. So during this flat spot, only the interparticle distance increases, the speed does not. So what would we see in the liquid? We would see bubbles coming up. We would see bubbles present throughout the volume of the liquid, because with boiling, heat is added usually at the bottom or maybe around the container, but the entire container, the entire mixture, entire substance is able to reach boiling point, unlike evaporation, which occurs just at the surface. So we would see brown gas collecting, and we would see bubbles throughout. Going on to number 9 then, during very cold weather, snow often gradually disappears without melting. Explain how this is possible. So this is a phase change. Number 9 asks about, it says, during very cold weather, snow often gradually disappears without melting. Explain how this is possible. Well, during very cold weather, air tends to be very dry. Water doesn't stay in the air easily. So during this very cold weather, we tend to have low air pressure. And so with this pile of snow, and these X's are representing the water molecules in snow, remember these snow particles have constant motion. And if some of the particles from below hit one on the surface just right, or if you have wind coming by, which we often do during cold times, any of these surface snow particles or water particles can escape, and they're going to escape to become water vapor. Normally, they won't have the opportunity to escape until they had the interparticle distances had increased enough to decrease the intermolecular forces. But because of that cold, dry air, that low air pressure, now you'll have some get popped loose, just like it does in evaporation. But in this case, it's sublimation and going right from a solid to a gas.